Good afternoon, everyone. My name is Mahika Karthe, and this is my ISC2 activity for flight dynamics. And the topic is longitudinal, lateral, and directional stability. So, seeing the contents of the presentation, we'll be seeing what is stability, overview of the axis of the aircraft. Then we'll be seeing the three types of stability, that is longitudinal stability, lateral stability, and directional stability. Then we'll be seeing its importance and its effects on the aircraft's performance. So, beginning with what is stability? Stability in an aircraft refers to its ability to return to a steady state or equilibrium after being disturbed from its original attitude, such as changes in pitch, roll, or yaw. Stability is a crucial aspect of aircraft design and operation to ensure safe and controlled flight. So here is an image below which shows the stability. I'll be explaining the image. So to achieve the stability, designers use various aerodynamic and structural features, including the placement of wings, tails, and surfaces, and the center of gravity. Additionally, control surfaces such as ailerons, elevators, and rudders play a role in managing stability. So now this diagram shows the different flight situations of an airplane. The top left image shows the plane in trimmed flight, which is where the forces of lift, weight, thrust, and drag are all balanced. Plane is flying in a straight line because all the forces are cancelling out each other. The other images show what happens when the plane is disturbed from trimmed flight. In the top right image, the plane is disturbed by a nose-up movement which causes the plane to pitch up. However, the plane is statically stable, so it automatically generates a restoring nose-down movement to bring the plane back to the trimmed flight. The bottom left image shows a statically unstable airplane. When the plane is disturbed by a nose-up movement, it doesn't generate a restoring movement. Instead, the nose-up movement makes the plane pitch up even more. This can be dangerous because it can lead to a loss of control. The bottom right image shows a neutrally stable airplane. When this plane is disturbed by a nose-up movement, it generates a restoring moment that is just strong enough to bring the plane back to trim flight. However, the restoring moment is not strong enough to prevent the plane from oscillating slightly around trim flight. So now moving on, these are the three primary axes shown passing through the center of gravity of an airplane, as we can see in this image. The first is the roll axis, also called as the longitudinal axis, which runs from the wingtip to the wingtip perpendicular to the fuselage. Then the next is the pitch axis, also called as the lateral axis, which runs from the nose to tail perpendicular to the wings and the roll axis. Then the third one is the yaw axis, also called as the directional axis, which runs vertically through the center of gravity perpendicular to both the axes. Now we'll be seeing the three types of stability, and the first one is longitudinal stability. So longitudinal stability involves stability around the aircraft's lateral axis. The longitudinal stable aircraft will tend to return to its original pitch attitude after a disturbance, such as a gust of wind or a control input. Stability in its axis is crucial for maintaining a constant airspeed and preventing the aircraft from pitching uncontrollably. The x-axis is labeled as angle of attack alpha, which is the angle between the oncoming airflow and the airplane's wing chord line. The y-axis is labeled as pitching moment coefficient. Pitching moment coefficient is measure of the rotational forces acting around the airplane's pitch axis. A positive pitching moment coefficient means the nose wants to pitch up, and a negative pitching moment coefficient means the nose wants to pitch out. Moving to the next part, which is lateral stability. The lateral stability involves stability around the aircraft's longitudinal axis, that is the wingtip to the wingtip. A laterally stable aircraft will tend to return to its original roll attitude after a disturbance. Proper lateral stability helps prevent uncontrolled rolling motions. The dihedral angle which is the angle between the two wings when viewed from the front, also plays a role in lateral stability. When the glider rolls to one side, the wing on the lower side has a higher angle of attack and therefore generates more lift. This creates a rolling moment that counteracts the initial roll and helps to bring the glider back to level flight. Then moving to the third type, which is directional stability. Directional stability involves stability around the aircraft's vertical axis, nose to tail, through the top of the fuselage. A directionally stable aircraft will tend to return to its original yaw attitude after a disturbance. This stability is crucial for maintaining a straight flight path and preventing uncontrollable yaw. To maintain directional stability and prevent the yaw from turning the airplane uncontrollably, the pilot deflects the rudder to the right. This creates a side force asymmetrical drag on the vertical stabilizer, countering the yawing moment from the engine failure. Directional stability ensures the airplane maintain its heading despite side forces or disturbances. In this case, the engine failure disrupts the symmetrical airflow of thrust, but the pilot's use of rudder demonstrates the importance of directional stability design features. Now, moving on to the importance, stability is a fundamental aspect of aircraft design that directly influences the safety, efficiency, and performance of an aircraft. Striking the right balance between stability and maneuverability is a key consideration in aircraft design to meet the specific requirements. The importance of stability in an aircraft cannot be overstated as it directly affects the safety, control, and performance of the aircraft. Now, in this slide, we can see what are the factors that affects the stability. First is controlled flight, then maneuverability, efficient fuel consumption, navigation accuracy, reduced pilot workload, safety and emergency handling, structural integrity, stall and spin characteristics, pilot comfort, adverse weather handling, compliance with certification standards. Thank you.